Have you ever seen a headline about some amazing new study and just wondered, how do they really know it works? How do scientists tell the difference between a real breakthrough and just a random coincidence? Well, stick around because we're going to pull back the curtain and look at the secret weapon they use to separate fact from fluke.
Okay, so let's paint a picture. Imagine researchers announce they've created this revolutionary new drug for weight loss. The first test results come back, and honestly, they look almost too good to be true.
I mean, look at these numbers. The people in the study, on average, went from 90 kilograms down to 60. That's a 30-kilo drop. You'd think, wow, this is a miracle cure. But for a scientist, this is where the real work and the real skepticism kicks in.
Because they have to ask the single most important question in all of science. Was this incredible result actually because of our drug, or did we just get really, really lucky with the people we picked for our study? Answering that question is everything.
This brings us to the first and most fundamental rule of good science. It's the assume nothing rule. Before you can prove something is real, you first have to start from the position that it's all just a big coincidence.
Now, this idea has a fancy name, the Null hypothesis, but don't let the name scare you. All it means is that you start by assuming the most skeptical, boring possibility is true. In our case, the Null hypothesis says our new drug is a total dud. It does absolutely nothing. And that incredible 30-kilo weight loss we saw? Pure dumb luck. The scientist's entire job is to gather enough evidence to prove that skeptical idea wrong.
The best way to think about this might sound familiar. It's the scientific version of innocent until proven guilty. In science, a new idea or a new drug is assumed to have no effect until the evidence against that idea is so strong, so overwhelming, that you have to throw it out and accept that you found something real.
So, why all the doubt? Why can't we just trust that initial result? Well, the problem, the villain of our story, really, is something called sampling variation. Just think about it, right? Scientists can't test a new drug on every single person on the planet. Of course not. They use a smaller group, a sample. But here's the catch. No two groups of people are ever exactly the same. So if you run the exact same experiment with 3 different groups, you're going to get 3 slightly different results, just because of random chance. And that's the problem.
Let me show you what I mean. Let's imagine we run our weight loss study not once, but 3 separate times, with 3 totally different groups of people.
Okay, so in our first test with sample A, we get that fantastic 30-kilogram drop we saw before. Looks great.
But then we do it again. With sample B, the average drop is a little less impressive, say 25 kilos. Still good, but different.
And in our third try with sample C, the result is even better, a 32-kilo drop. Now see what's happening? None of these results are wrong. They're just fluctuating. This is that random noise, that sampling variation, that scientists have to cut through.
So here it is, the big challenge. With results bouncing around like this, all due to chance, how in the world do you find the actual truth? Well, it turns out we can use math to figure out the odds. Yep, scientists have a special mathematical tool designed to do exactly this. It allows them to calculate the precise probability that the results they saw were just a complete and total fluke.
It's called a test of significance, and its whole purpose is to answer one single question, and it goes right back to that skeptical null hypothesis. The question is, if our drug was a total fake, if it did absolutely nothing, what are the chances we'd still see a result this amazing just from random luck?
I really love this way of thinking about it. A significance test is basically a mathematical way of calling a bluff. You're looking at the results and you're asking the universe, are you for real or are you just bluffing with a lucky hand? This test calculates the odds.
So, once you have that probability, that magic number, the scientists can finally step into the role of a judge and deliver a verdict on their findings. When you lay it out, it's a really logical step-by-step process. First, you assume it's a fluke. That's your null hypothesis. Then you go out and get your data. Next, you run your test to calculate the odds of that fluke. And finally, you make the call.
And it all comes down to this single decision. If the probability that your result was just a random fluke is really, really low, then you get to reject that it's a fake theory. And that's when you can officially declare your result is statistically significant. But if the probability of a fluke is high, well, you just can't rule out random luck. You fail to reject the null hypothesis, and your result is declared not significant.
Of course, it's not quite a one-size-fits-all kind of deal, Just like there are tons of different kinds of scientific questions,
There have to be a lot of different tools to answer them properly.
Which brings up a really important question. How does a scientist know which statistical wrench to pull out of the toolbox? Choosing the right one is absolutely critical to getting a valid answer.
The choice really depends on the ingredients of your specific study. Are you measuring hard numbers, like weight in kilograms? Or are you looking at categories, like whether people improved or did not improve? How big is your group? How many different groups are you comparing? All these factors point to the one correct test for the job.
This chart here gives you just a tiny peek into that toolkit. Now, please don't worry about the names, ANOVA, t-test, chi-square test. That's not the point. The big takeaway is that this is a very structured, logical process. For every type of question, there's a purpose-built tool designed to give the right answer. It's not a random guess.
So really, the biggest thing to remember from all this is that behind every major scientific claim, there's this intense, mathematical battle against random chance. So the next time you see a big headline about an amazing discovery, you're armed with the most powerful question you can ask. Okay, the result is interesting, but is it significant?